My name is Ryan Jones, and I'm the co-founder of Evolved Energy Research, a small consulting company based in California. In this section, we're going to talk about transmission, energy storage, and grid integration of renewables. We expect two basic things from our energy services. The first is that a service needs to be reliable, and that really means that supply must match demand at all time scales longer than a few seconds. And even within a few seconds, the imbalance between supply and demand must be quite close. Second, we expect service to conform to basic standards for voltage and frequency, and we call this power quality. The problem with poor power quality is it can reduce the lifetime of appliances and equipment, cause flicker with lights, and have other unintended consequences. So these are the two aspects that we want to keep in mind as we talk about the impacts that renewables can have on the grid. Reviewing really the options here for building a low-carbon system and ignoring hydro and biomass, which don't have the same technical potential, we have three basic options. The first is fossil fuels with carbon capture and sequestration. Theoretically, these plants can really operate much like power plants do on the grid today. Second, we have nuclear, which while less flexible, can still be operated flexibly enough to meet the two balancing criteria from the prior slide. And finally, we have renewables, such as wind and solar, which while favorites for decarbonizing the electricity system, they each present unique challenges for balancing. Why exactly are renewables a challenge? First, their output is variable, meaning it is not controllable and oftentimes it will change rapidly. And second, their output is uncertain, meaning it's not possible to predict when exactly they will be and will not be producing electricity and how that will change in the future. And so this can cause real problems scheduling power plants or electricity trading. Third, the locations with highest resource endowment are not necessarily locations that overlap with where we have demand or where we have existing electricity infrastructure. Finally, there are some technical reasons why conventional power plants with synchronous generators are different than renewables which use power electronics. When we think about these issues of balancing load, those issues can occur over a certain length of time and in a certain place on the electricity grid. So mismatch between supply and demand or power quality issues can happen over many different time scales, shown here on the x-axis, and they are also specific to a location on the grid, shown here on the y-axis. On the distribution system, the problems that occur from high renewable penetrations happen only when renewables are physically located on the distribution system. And these issues arise predominantly because most distribution networks have been designed with the assumption that there is only load on the network, not generation. To categorize these further, they really fall in one of three categories, which is they're related to power quality, wear and tear on utility equipment, or safety when it comes to utility workers. With new distribution system equipment or good control schemes for distributed generation, we can solve each of these issues, but fixes can be expensive and therefore, effectively, you can have limits to the amount of renewables that can be deployed on any single network. So next, we have challenges from renewables that occur on the level of individual utilities or balancing authorities. Often these issues touch on the dispatch and operation of conventional fossil generation that gets used to meet the difference between load and renewables. The good news is most systems have been shown to have a fair amount of latent flexibility in their generation resources, so that moderate renewable penetrations have been accommodated without too much expense. And much of this will depend on the age and the type of generation on the system to begin with. At the utility level, as penetrations of renewables increase, the time scale of the dominant balancing challenge tends to increase from left to right. So starting with regulation and area control error, kind of on the left, and as renewable penetrations build, we move into the bubbles to the right, ending with minimum generation constraints and increasing the number of generator starts. Finally, at the interconnection level, which may encompass dozens of balancing authorities, the challenges associated with high renewables relate to the imbalance between load and supply across many different timescales. The types of renewables deployed, whether wind and solar, and other factors can significantly change the patterns of energy imbalance and therefore the type of solutions deployed. So now putting everything together on one chart here and thinking about the enablers for high penetrations of renewables, it's important to think about how they map onto these dimensions for load balancing. So now adding to this two solutions that we are talking about now, energy storage and new transmission, or more generally, transmission and coordination between balancing authorities. Some of these problems may be solved with storage, others may be solved with transmission, and some may be solved using both, but sometimes at very different costs. So not all of these issues occur on all systems, and oftentimes can be minimized with smart deployment of renewables. So next, let's focus on this bubble in the upper right corner where we show seasonal energy imbalance that's not easily solved by either storage or transmission, and talk about that issue in more detail. So the basic issue is that assuming the deployment of renewables was your dominant strategy for decarbonization, the production of energy across the year from wind and solar will probably not line up with when during the year the energy is actually consumed by customers. And so in this example here, we're showing what it would take to meet 100% of the eastern interconnection of the US's grid in 2015 with wind and solar. So this is 40% solar and 60% wind. From this, we can see a couple things, which is that in the spring and fall, we have huge quantities of surplus energy. And then in the summer, we've got a large energy deficit, and we really have no effective way of shifting energy from one season to another. This is an issue if you think about energy storage being used to basically solve this problem, because for an energy storage resource, you would be charging twice a year, once in the spring and the fall, and you would be discharging only one time per year in the summer. It would be a huge amount of energy storage required to meet that demand, and therefore it would really be prohibitively expensive. The USCDPB reports, which have been mentioned already, talk more about this issue and some of the different solutions that we've seen in our research to help deal with this. Thinking further about designing solutions to balancing problems, deploying these balancing solutions intelligently is important because the same solution isn't going to work everywhere. It's also important to recognize that curtailment of renewables in some quantity is actually optimal and gives us the lowest cost energy system. This is a good thing to keep in mind because a gold-plated system that integrates every last megawatt hour of wind or solar is not necessarily desirable. So to summarize, when you look at the details of grid balancing, the issues are diverse and complex and must be understood together with the particulars of any specific power grid. But we do have many effective solutions for the problems posed by renewables, and this ultimately makes it more of an institutional and economic problem rather than an insurmountable technical challenge. Finally, balancing solutions must be tailored to the specific location and timescale of balancing problems because no solution is universally effective. So if we think about using storage alone, it is likely that that will be prohibitively expensive on the system. Using transmission alone is not going to solve any interconnection level problems. Using flexible load alone will probably degrade service, and while some renewable curtailment is rational, using it alone is likely very inefficient. But if you look around the world at many of the locations where we have particularly high penetrations of renewables today and where they're pushing higher, places like California, Germany, Spain, Denmark, those are each places where some combination of these four strategies is being used effectively today, and many of them, storage in particular, and also flexible load, are becoming kind of wider spread and also cheaper, which really leads us to believe that many of these problems that I've presented from renewable integration are ones that are definitely surmountable in the near future. So some combination of these strategies is technically feasible and is shown to be economically feasible in many locations around the world today.